Hello and welcome to Module 3 of video lecture of Chapter 10. As I said in my previous video during Module 2, Chapter 9, I said that Chapter 10 is a continuation of Chapter 9, and I also kind of covered small topics from Chapter 10. So there is really nothing new here, with just a continuation of what we have been covering in Chapter 9. And it's basically in the subject of conservation of energy. So let me just make a quick review of what we have covered during the previous chapter, and then basically most of the lecture is just going to be doing problems. I have a couple of examples from the book, and I have some example or problems from my lecture notes. And then you shouldn't have a problem finishing the homework without any issues. So anyway, let's just make a review here quickly. So we said that we started by talking about work, and we said that work it has different versions, different expressions. One of them, or the formal one, is that it is the negative integral of the force dx. Okay. This is the most general one, such as the force is a function of position. That's why you take the integral with respect to in dx rather than dt and so on. Okay, and also we talked about the work energy theorem, and we said that work is equal to the potential energy, and the difference in potential energy, and also equal to the difference in kinetic energy. Remember that? So these are the formal equations. Also, I talked just a little bit about the relationship between the force and the potential energy. Look at it. Look at this equation, the work equation here. So we have work is equal to minus integral f dx, and then we said that the work is the potential energy delta U. So if I want to solve for f, basically f would be something like that, minus du dx. Make sense? And this is a very important equation in classical mechanics, and this is the definition of what is called the conservative force. Conservative force. In other words, if you are given a potential function and you are asked to find the force, just take the negative derivative with respect to x, and that will give you the value of the force. You see what I'm saying? Now, let me use this one to calculate something. And by the way, the minus here means, do you remember what the minus sign means? I don't know if I talked about it or not. The minus sign here means, let me go back to the total energy. Remember that total energy is equal to what? Kinetic plus potential. Now, is it possible for a mechanical system, while it's in motion, or is it possible for it to have the kinetic and the potential increase at the same time? The answer is no. Always, whenever there is an increase in kinetic, that means there is a decrease in the potential. The converse is true. If there is an increase in the potential, there is a decrease in the kinetic. Why? Because that decrease and the increase will be always equal in such a way that E will always be constant. This is important. You see what I'm saying? So this E here is a constant, and that's really the statement of the conservation of energy. Conservation of mechanical energy, let's say. Okay. So this means, so any increase in kinetic energy implies a decrease in potential energy. You see what I'm saying? Any decrease in kinetic energy implies a increase in potential energy. This decrease and increase thing is given by this minus sign. This is the meaning of this minus sign, or this one. You see what I'm saying? So when we say that work is equal to delta K, and more properly to just say minus delta U, because this delta U means that an increase in the kinetic is a decrease in potential and so on. Okay, that's the meaning of it. Okay, let me give a very quick example, and then I want to explain one more thing before we go into the problems. And this is example example 10.1 in the book. Oh, I can just access the example from here. Let me look at the hard copy. Just want to see what page. Sorry. Third page. Should be here somewhere. Sorry about that. It's on page 234. Should be on this page. There it is. Okay, simple example says Raphael uses a slingshot to shoot a 25-gram pebble straight up at 70 meters per second. How high does the pebble go? Okay, simple, very, very simple problem. So basically, in this problem, we have example 10.1. So we have here is the let me make a free body diagram of this thing. So here's the ground, and this guy is shooting with his slingshot a pebble. The initial velocity of the pebble is that what he said? Yeah, the initial velocity is 17 meters per second. And how high is it going to go before it falls back? In other words, he wants the height here, okay? I'm trying my best to draw the height in a vertical way. There we go, okay? Now, of course, we can use kinematics, right? I mean, that's easy. You just use which kinematic problem? Which kinematic equation? Probably the second one, this one. Let me use kinematic very quickly, and then we'll use energy. So I can use the second one, this one. V squared equals V naught squared minus 2gh, correct? Of course, the velocity here is 0 because it stopped measuring the maximum height, so that should be 0. And therefore, the height in this case would be something like V squared over 2g. You see what I'm saying? There we go. That's the answer if I'm going to use kinematics. Now let me use energy. Same thing. So what I ask, I basically always, you look for two positions. So this position here and this position here, the energy is conserved, right? And remember, energy is what? K plus U, always K plus U, K plus U. Remember that. Okay, so if it is K plus U, so K plus U here equal to K plus U here. You see what I'm saying? So let me call this position A, this is position B. So E at A is equal to E at B. So we have a kinetic energy at A, but we do not have potential, correct? Why we don't have potential? Remember I told you, potential means height. If there is height, there is potential. No height, no potential. Kinetic, if there is speed, there is kinetic. No speed, no kinetic. It's really that simple. You got that? So potential is linked to height. Excuse me. And kinetic is linked to speed. Okay. So here we have speed, obviously, but there is no height because this is the ground and this is my datum. Remember datum? So I'm assuming my datum is here, the height is 0, and therefore the potential is 0. Okay. At B, however, what happened? Well, it reaches the maximum height. That means the pebble stopped. So that means no kinetic. Remember? Velocity, if there is speed, there is kinetic. Well, no kinetic. So here we have K plus U, but this time the kinetic is not there. We only have potential equal to mgh. This is the h we're looking for. And the kinetic here, down there, is going to be 1/2 mv naught squared. And the masses cancel out. And I'm going to solve for the height. And that will give me v naught squared over 2g. And there we go. We got the same answer. You see what I'm saying? Same stuff. Good. Okay. Let me move. Let me just talk about one more topic, and this is section 10.3 in the book. It's called elastic potential energy. I can explain it in a few minutes. The book goes on and on for like 3-4 pages on this stuff, but it's not really that complicated. Elastic potential energy. When you hear the word elastic, think of a spring or a rubber band or something that's stretchable, if you know what I mean. So if you remember Hooke's law for the spring, right? Hooke's law for the spring says F equals minus kx. Remember that? The k here is the stiffness constant. And of course, x here is the displacement, or if you will, the stretch, or the compression. It's not the length of the spring, you know what I mean? Let's say I have a spring. Here is the floor, here is the wall, and I have a spring that is relaxed. It's not stretched, it's not compressed, just sitting there, okay, relaxed. X is 0. So X is not the length of the spring. I don't care about the length of the spring. You got that? It is the stretch itself. So if I stretch the spring from here all the way to here, now the spring is here. So X is not the entire length, it's just that stretch. Okay? In other words, X here, the displacement, is from the relaxed position of the spring. This is the relaxed position. I don't care for it. I don't care about the length of it. It doesn't really matter. Whether it's very short, it doesn't matter. Okay? What matters as far as springs are concerned is the displacement and how stiff the spring is. This stiff is called Hooke's constant or spring constant. I like it. I like to say the stiffness constant, and it's measured, of course, in Newton per meter. Okay, to give you a sense of it, the stiffness of the spring of the coiled spring that you see underneath your car, that's about, if I remember correctly, 20,000 Newton per meter. Okay. Very, very large. You couldn't stretch it or compress it with your own hand, if you know what I mean. Okay. So anyway, so if I want to find what is the corresponding, so this is a force, and it's a conservative force because it's a function of displacement. And if I ask, what is the corresponding potential energy? Remember we said that the potential, delta U, which is equal to the work, right? And that's equal to, or rather minus U, equal to the work, and it's equal to minus the force dx, right? So if I would plug this one in here, and that's going to be minus kx dx, see what I'm saying? So that would become 1/2 kx squared. You see what I'm saying? So in this case, delta U, or the potential energy U, is equal to that. Got it? So what does that mean? It means that if I have, let's say, let me give you an example. Let's say, for example, I have, let's say there is a wall, and this is a floor. And let's say I have a spring here. Let's assume it's relaxed, okay? It's not stretched at all and just sitting there. And then I have here, far away somewhere here, I kick a puck or a box or a block. Let's make it a block, okay? A block of mass M, okay? And I, let's say, for example, I kick it. Now it's moving with some velocity v naught. Okay, let's say this. Let's assume that this velocity is constant. Okay, I mean frictionless surface. Assume it's frictionless surface, and this is the spring of stiffness constant K. Okay, so the block will hit the spring, and then it will compress the spring. So here is the second picture. Let's assume that at the instant of maximum compression, okay, at the instant of maximum compression, right there, right before the spring or the block rebound, okay, right there. So that means this maximum compression is X here. Remember, X is stretch or compression. And let's assume that this X is given to us. The question is, what is the speed? What is the original speed of the block? Let's say right before it hit the spring. In other words, you want V naught. Okay? And let's assume X here is given to us. Let's assume it's equal to X naught. So K is given to us, whatever number you want. X naught is given to us, say 3 centimeters, whatever. And then the mass of the block is given to us, if it's important. Okay? Now he's asking, what is the original speed of the block? Well, how do we do it? Again, we use conservation of energy. You ask the question, you look at the entire dynamical system here, all of that. And you say, what is the total energy of the system here? So basically, you want to add up all the energy there, mechanical energy. Well, the spring is relaxed, so there is really no potential energy. See, the potential energy of the spring is given by this expression right here. You see what I'm saying? 1/2 kx squared. But there is no 1/2 kx squared because it's not compressed or stretched. You see what I'm saying? But there is kinetic energy of the block, and that's it. So basically, E before collision is equal to 1/2 mv naught squared for the block. Remember, the block has a mass m. M is given to us. The v naught is the unknown. Okay, that's what we are trying to find. Now, at the moment of compression, maximum compression right here, well, nothing is moving, right? And what happened is that all this kinetic energy has converted into potential energy. Spring potential energy, this one. All of it. You see what I'm saying? So here we have the energy after collision is all of it 1/2 kx squared. In other words, all this energy here has been given off to the spring to be compressed by a displacement x naught. Okay? So by the conservation law, those two must be equal. Halves cancel out, and then I can solve for v naught. And that will be k over m x squared to the power of 1/2. And then whatever the number they are given, and that's how you solve the problem. Very simple. I hope it is simple. Okay. Here is a more difficult one. The pendulum. The simple pendulum. Pendulum. All right. Let me brighten the screen a little bit. It's a little bit dark for me. Better. I hope it's better for you as well. All right. So the simple pendulum, when we say simple, it means it's the word simple means that I have a pendulum that has a string and a bob, and the string is rigid. It's not elastic. It's not like a rubber band or something. It's not changing in length. Okay, so you have a constant length L, and then you have a bob. This is the bob, the mass, whatever it is, and that bob is not changing. For example, let's see an example of a pendulum that is not simple would be something like, imagine I have a pendulum. Here is the length and is hooked up to a spring. Assume that. And then let's say it is also hooked up to a bucket, or let's say a bag, and let's say a bag is filled with, say, sand. Okay, and let's say the bag is punctured and it's keep leaking sand as it swings to and fro. So what's going to happen here, the spring will be moving to and fro like that, and the mass is decreasing. And it's not just that, because of the spring is actually also stretching up and down like that. So it's kind of a weird motion. It becomes pretty complicated. You can't really solve it with basic elementary physics that we are studying here. You need something more complicated, such as what is called Lagrangian dynamics or Hamiltonian dynamics. It becomes a pretty complicated problem. In other words, it's not a simple pendulum anymore, but that's a simple pendulum. That's why they call it the simple pendulum. Okay, back to this problem that we have. So let's say I have a pendulum, simple pendulum that is, and let's say here's the pendulum. So it's I'll try my best to make it. There it is, and it is. Let's say it's swinging like that, and let's assume that I want to know, so the pendulum as it swings, okay, so it reaches a maximum height here, right, and then it falls back again, right, so it oscillates back and forth. So this is the maximum height reached by the pendulum. If I assume that the lowest height is here, the lowest point, so this is the height reached by the pendulum before it returns back, you know what I mean? We'll call that h. And of course here, there is no height, see that? I mean, here's my datum right here. Datum means that the height is 0, which means the potential is 0. Remember, height and potential are linked. So here I have 0 potential, okay? Let's assume the length of the pendulum is L. The question is, well, hold on. So so the pendulum reaches a maximum height here and it stops. What that means is that all the kinetic energy of the pendulum, all the motion energy of the pendulum has been converted into potential energy. So the pendulum here is all potential. However, the pendulum here is all kinetic because there is no height. Make sense? So here, the pendulum is all potential energy. Here is all kinetic energy. Okay? And the question is, what is the velocity of the pendulum at the lowest point? That's the question. All right, this is the problem that we're going to solve. It's not a difficult problem, but again, you want to use conservation of energy to do it. Okay, before I do that, I want to know, let's say this height is not given to me, but let's assume that this angle theta is given to me. So theta is given to me and the length of the pendulum is given to me. These are known to me. So known L and theta. Okay? And then now what I want to do is, and mass is not known. Maybe, actually it's not important. I'll show you in a minute why. But let's say those are known. And now I need to find what is the velocity v naught. Okay? How do we do it? Well, okay, we just build it up. So we call this position A and position B. You don't need to call them that, but I'm just saying it just to clarify how things can be solved. So at position A, so it is k plus u. Of course, there is no u here because there is no height. So it's all 1/2 mv naught squared. And this is basically what we're trying to find. We want to find v naught. Okay? So I got that. Fine. Now, let's go to position B. Well, at position B, there is no velocity. There's no, the pendulum stopped moving. So the total energy, at B is equal to k plus u, but k is 0, correct? So it's all u, and this EB is equal to mgh. H is this height. But what is this height? I don't know. I need to find an expression for the height. Find expression for the height. Okay? Here is how you find the expression. Let me show you. It's all geometry. I'm going to draw the pendulum again. So I'm going to go, here is the pendulum. Here's the pendulum at the lowest point. All right, here's the ball. I'm just going to draw it like that. And of course the pendulum is going up like that. And let's assume the pendulum now is here. This is the maximum height. Okay? And of course this is the datum. And this is the height. Is that right so far? So we said that the length of the pendulum is L. Here is the length of the pendulum. Okay. Now, again, I need to find an expression for the height. How do I do it? Well, here is a little trick for you. Theta. Please learn it. You're going to see it if you take static and dynamics. If you're a mechanical engineer or civil engineer, you're going to take those courses, statics and dynamics. And you got to see this stuff. Trust, I took those courses in the past, back when, and I remember using this this technique. So learn it once and for all. How you find that expression for the height of a pendulum, the pendulum bob. All right. So far so good, everyone. Okay. Now look at this. I'm going to make a little trick. Look, if I make a triangle here, so I got this triangle right there, this one, okay, right here. So what is this height? Or what is this length from here to here? What would that be equal to? Well, that will be, if this is L, so it's going to be L cosine theta, right? Yeah, if I can make it. There we go. Okay? You agree with me? Well, the height is right there. So therefore, the height is really L minus L cosine theta. Is that okay? So the height is L 1 minus cosine theta. Might as well memorize it if you want. I've been memorizing it for many years. I don't need to derive it every time because I've seen it many times. But that's basically how you measure the height of the bob. Okay, now go back to our energy expression. We got to equate E sub B and E sub A together. You see what I'm saying? With this expression for the height right here. You got it? So let's do that. So here we have 1/2 mv0 squared equals mgh, but this h is right now is that. The masses cancel out. Now you know why the mass is not important, right? So we have here v0 is equal to the square root of 2gl 1 minus cosine theta. And there we go. We got the velocity. Remember I told you we are assuming that theta and L are given to us. Right there. So we just plug it in and then we would find the velocity at the lowest point, that is. Okay. Okay, great. One more. This is problem number 11. I think it's homework, but it's really easy. For those of you who have taken physics in high school, it should be a pretty trivial problem. Oh, I keep forgetting. We have a book here. Let me find it. We are chapter 10. Go to the problems. Number 11. Not this one. I think it's. Here we go. Here. There we go. This problem, I'm sure you've seen it. A lot of you have seen it before. Okay. It says 11 right there. Okay, it's right here. This drawing right there. Okay, so it says, whoops. He says a 1,500 kilogram car. Here it is, right there. Let me write it down. So you have something like this. Looks like it goes up higher. Right there. That's a gas station here. All right. Here's the car. Nice looking car of a height of 10 meters. And then the height of the gas station is 15. I haven't read the problem, so sorry about that. There we go. Okay. It says, so I have a mass of a car is 1,500. Traveling 10 meters per second. So the velocity of the car is 10 meters. Let me call it 10 V0. Suddenly runs out of gas while approaching the valley shown in the figure. The alert driver immediately puts the car in neutral, all right, so that it will roll. What will be the car's speed as it coasts into the gas station on the other side of the valley right here? You got that? So, all right, simple problem. So here basically what's the speed of the car right here? I'm trying to draw a car here without it falling off the cliff. There we go. He wants the velocity here. Let's call this position, what should I call it? Position B, okay? So he's looking for V sub B, okay? He gives me V naught here. Got it? So, how do we do it? Well, just conservation of energy, right? You ask the question, let's assume this is position A here. So you ask the question, what is E sub A? And you equate it to E sub B. And then you just work it out and solve for V sub B. It's that simple, right? You see what I'm saying? Excuse me. So E sub A, well, what do we got? Do we have height? Yes. Do we have speed? Yes. Therefore, we have potential and kinetic. So mg 10, is that okay if I just say that? Plus 1/2 mv squared. 1/2 mv naught squared. I'll come back to it. V naught is 10, right? Equals to, what's going on at B? Well, that is height, so that will be mg 15. Is that right? Plus 1/2 mvb. How do I know that is velocity there? Well, that's what he says. He said, what will be the car's, what will be the car's speed as it coasts into the gas station? So he's not saying that it's going to stop here. There'll be some kind of speed. So let's calculate that speed. There we go. Simple. So the masses cancel out. So this mass that he gives us really is not important for this part of the problem. And so I can move this over here. So that's going to give, if I move this over here, yeah, I can do that. Because remember, I'm solving for V sub B. That will give me minus 5g, correct? And then plus 1/2 times 10 squared equals 1/2 VB squared. Are you guys following my algebra? That's going to be minus 5g plus 50, correct? 100 times that is 50. Multiply this by 2 from that equals VB squared. Is that okay, guys? Okay. So in this case, so VB is equal to the square root of 50 minus 5g, I think it's 49. Use my calculator. 5 times 9.8, 49. Oops. And so, times 2, sorry. Times 2, yes. So in this case, this give me 1 square root of 2, and that will be, what is it? What's the square root of 2? 1.414, is that right? Square root of 2, 1.41. 1.41, I believe so. Square root of 2, 1.414, yes. 1.414 meter per second. And there we go. I have the velocity of the car. Got it? Okay. Let's do something a little bit harder. How much time do we have? I mean, how much time have I been babbling? I don't know. I can't read it from the bottom here. Oh well, probably half an hour or so. Okay, I have at least 3 more problems to do. And they're going to progress in difficulty. Okay, now let's go into some serious problems. Okay, with some serious difficulty. I'm not going to be using the book now. I'm just getting this out of my notes. So let me make this disappear there. Oops, I'll just keep it here. Okay. All right, here's a problem for you. You know, let me do this one first. Yeah, I'll do this one first. All right, here's a problem. Okay. So you have, here is a wall, and here is a surface of a table, and this is the edge of the table right here. We have a pulley system. I'm trying to be as slow as possible to get on a decent drawing. Okay, and then I have a block here. Okay, I'm going to call it block 1. And the block is hooked up to a spring. stiffness constant K, and the block is hooked up also to the pulley, or there is a, I'm sorry, it's hooked up to a cable, and the cable runs over a pulley like that. And then underneath here, you have a mass 2. And there we go. This is our dynamical system. Okay. The question is, oh, there is also friction between the block and the surface of the table. Okay, there is friction. So friction of coefficient of friction mu, and we're supposed to find the mu value. Okay. So the question is this, or the statement of the problem: M2 falls h, a distance h. Okay, so it falls a height h, if you will. Okay, so M2 falls a distance h and stops. Okay, what is the value of mu? And you are required to use the energy method. Okay, we're not. We can use the force law, but we have to use the energy method. Okay. How do we do it? All right. So here we have 3 parts for this dynamical system. We have mass 1, we have the spring of stiffness constant K, and we have mass 2. First thing you need to do, and I think I told you this in class, is that you need to run a film in your head. Look how the system is moving. Well, how is it moving? Well, here's how it's moving. The M2 is going to move down this way, right? And M1 is going to go this way, and the spring is going to stretch this way. So basically, the mass is going to move a distance x. The spring is going to stretch a distance x, the same as that. Yes, everyone? And do you agree with me, this value x is exactly the same as h? Make sense? Think about it for a minute. So here's my quick thoughts. X is equal to h. Makes sense. Otherwise, if it's not, it's gonna the cable is gonna slack. You see what I'm saying? It's gonna be like that. So we don't want it to be that. All right, that's the first thing. Second, now he says use the energy method, so we don't have a choice. Okay. What's causing the motion? What is? What's causing the motion? The one that is causing the motion is block 2. You agree with me? Kind of a, block 2 is heavier than both of, heavier than block 1, and so it's the one that is moving everybody, moving those two together. Okay, so this is how I am seeing it, is that block 2 is the one that is causing the motion. Imagine that in the beginning, I had my finger or my hand right under M2. I'm forbidding it to moving, then I let go, then the block is gonna come down by a height or distance h, and then as a result of that, block 1 is going to go this way, and the spring is going to stretch a distance x. Okay? Awesome. All right. So, what are the energies? Well, let's see. You agree with me that this loss in, okay, while I was holding my hand, the block with my hand, the energy on the block was all potential. Make sense? It's not moving. I'm holding it in my hand, for example. So it's all potential, and that potential is equal to M2GH for the block 2. And that's it. That was the only available energy for the system, assuming that the spring is unstretched yet. Okay, and the block is not. Now, when I let go, this loss in potential, it went from here to here. This loss in potential is equal to the gain of kinetic and spring potential here. Make sense? So it is a gain in the kinetic, But let's take the situation where now block 2 is here. The whole system stopped. Okay, so block 2 moves from here to here and stops. So what's going on here? What happened? Where is that energy? Well, energy has been lost through the potential and gained by the spring, and gained by what? Well, it gained by the friction force. In other words, there was work, remember work is energy, done by the friction. So here we have, this gain is 1/2 kx squared plus the friction force, the work done by the friction. The work done by the friction. What's the work done by the friction? Okay, work in general is Fx, right? Well, work done by the friction force, is Fx, where F here is the friction force. Okay? So here I can rewrite it again like this. M2GH equals 1/2 kx squared plus F done by the friction force, x. X is basically the displacement, which is equal to the displacement of the spring. I'm done with the problem. If you understand that, and we are done with the physics, pretty much. So now I need to find what F is. Well, what is F? Remember? F is mu n, if you remember. So if I take, remember the friction force is right here. There's the friction force. So this n here is the mg, right? I mean, if I have block 1, here's a block 1. So I got m1g, and this is the normal, right? So here, normal equal to m1g. We've done that a million times. So in this case, let me just go up a little bit. So therefore, the friction is mu n. So that's going to be mu m1g. Mu m1g. That's the friction force. So I'm going to take that and put it right there. So therefore, m2gh equals 1/2 kx squared plus mu m1g. I'm done with the problem. Now I just solve from mu. So therefore, mu, can I do it in one shot? m2gh minus 1/2 kx squared over m1g. And there we go. And then whatever number is given to us, we plug them in there, and then you calculate that. Got it? Okay. Good. One more topic I want to talk about. This is a very quick topic, and that is power. Before I do another couple of problems, power. So what is power? I think we talked about it in the past. Power is energy over time, or work over time, right? Or rate, this is how I like it, how I like the definition. Rate of energy dissipation. Rate, see the word rate? When you hear the word rate, remember in calculus, what does that mean? Rate means dy dx, right? Remember? Or dy dt. In physics, rate is with respect to time, okay? So the rate of energy dissipation per unit time, per second, or whatever, over time. Okay? So energy over time. You got that? I think, let me give you a quick example of that. Let's say you buy a light bulb. Okay, oh, sorry. The unit of the power is what? Well, it's energy per unit time. So the unit here is joule per second. And that's what we call watt. Big W. Okay? Okay. Now, let's say you buy a light bulb. Okay? And let's say the light bulb, let's say you buy a light bulb of 100 watt. What does that mean? It means that this light bulb is giving off 100 joule every second. That's the meaning of it. Joules of energy every second. Okay. In other words, it's dissipating. It's consuming the expenditure of energy. Okay. So that's the meaning of it. So think of the word power is the rate of dissipation or energy dissipation. This is a very good definition. I know your high school teacher taught you work over time. Fine, but that's not, it doesn't give you really a full definition, or it doesn't give you a feel for what power is. Power is the energy dissipation, you know? So it is the energy expenditure, you know, the spending of energy, the consumption of energy is the power, okay? That's why it's called a power company, because what do? They charge you on the expenditure or the consumption of energy, or consuming electric energy. This is what they charge you on. They charge you on the consumption of the energy, power. That's why they call themselves the power company, not the electric company, the power company, because it's all based on expenditure. Get that? Okay. So that's the meaning of it. Another way of saying, so we have power, and we say energy here. It could be thermal energy, it could be electric energy, it could be mechanical energy, it could be work. Any kind of energy you can ever think of, divided by time, is power. Period. And it has the unit watt. Period. Okay. Of course, for our case, we've taken a course in mechanics, so it's just work over time. It could be kinetic energy over time if you want to, or potential energy over time, whatever you want. Another way of defining it is that power is the derivative of the energy. How do I call energy? You know, let's call it E for energy per unit time. That's another way of defining it, or the derivative of the potential energy, or the derivative of the kinetic energy, whatever you want, or the derivative of the work. Okay. Now, whichever. Okay. So let's say let me use the last one here for simplicity. So here we have power is dW dt. Well, work is what? So I have d dt. Work is Fx in its simplest form. Okay, I just use the simplest form of work. Now we are assuming, if we assume that the force is a constant, we don't have to assume that, but we're just going to assume that. So I can kick it out because it's just a constant, so I can just put it here. I don't need to use the product rule. You see what I'm saying? So in this case, it's going to be F dx dt. Well, what is dx dt? It's velocity or speed, right? So Fv. And that's a cool expression for power. Force times velocity. Memorize it. If you've never seen it before. So there is a lot of definition for power. Here is a bunch of them. Here is another one here, the conceptual definition of it. Rate of energy dissipation per time. And there is another one. Force times velocity. It comes in really handy. Okay? If you take a course in E&M, power is IV. Current times voltage. There's a lot of expression for power. Okay? All right. I'm trying to think, why do I want it? I'm looking for that. Oh, here. Okay. Here's an example that has to do with power. It says an elevator car of mass 1,600 kilogram, okay, carry passengers of mass, a passenger one, I guess, of 200 kilogram. That must be at least 2 people. 200 kilogram, okay. A constant friction of 4,000 Newton retards the motion. Okay, retards the motion. He's asking the question, how much power must the motor deliver to lift the car with constant velocity of 3 meters per second. Okay? You can pause the video and read it again. Make sure you understand the problem. Okay? So here you have an elevator, and the elevator is that is suffering from friction. There is friction there as the elevator is going up the thing, of the chute, whatever. And the mass of the elevator by itself, empty, 1,600, 1.6 ton. And it's carrying, let's say, 2 passengers, 200 kilogram total. So you have a total of 1,800 kilogram. And this retarding motion is, or friction, is 4,000 Newton. Okay? How much power must the motor deliver? How much power that the motor have to expend, if you will? Okay? Or consume. How much power, energy, must consume to lift the car with a constant velocity of 3 meters per second. You got that? 3 meters per second, that's about 6 miles an hour or something like that. Okay? So how do we do it? Well, again, the best thing to do always, picture the problem. So I'm going to picture my problem. So I'm going to draw my FBD. Here is the 2 passengers. There we go. And here is the elevator cable. So the cable with a tension T, the mass, the total mass of the elevator, we're going to call it mg. And then there is a retarding motion. Well, that's friction. So I'm just going to call it friction. It's always opposite the motion. Here is the velocity or the direction of the motion. You see what I'm saying? Okay, so there we go. Here's a picture for us. So as the elevator is going with this velocity, 3 meters per second. You see what I'm saying? I'm sorry, I wanted to say that I just want to use this problem just to show you how to use power, but we're going to use the force method, okay? All right, so I'm going to use F equals ma. Of course, he said a constant velocity, so that means 0, right? There's no acceleration. Okay, so what are the forces? T minus mg minus the friction equals 0. Is that okay? And I mean, the motor is not the mg. Where is the motor coming from? The motor, this is the tension. The tension is coming from the motor. You agree with me on that? This is from the motor. Okay? This is coming from the motor. So that means the power delivered by the motor is this, the tension, coming from that. So the tension in this case is going to be mg plus the friction. The friction is just a number. It's right there. This is the friction right here. Just a number. You just plug it in. mg is nothing but the mass of the elevator plus the mass of the passengers. So that's just going to be 1,800, correct? 200 plus 1,600 times 9.8 plus 4,000. And there we go. For this, I can calculate the total tension delivered or tension given by the motor. So I can go 1,800, I'm using my calculator, times 9.8, and that's equal to that, plus 4,000. Answer, 5,809.8. So it's going to be 5,809.8. I'm sorry if you're hearing noise. I get some visitors here sitting with my wife, and I have the door closed, but they're making a little bit of noise. I hope it's not a distraction. Okay, so we have that. Here is the tension. Now I want to get the power. Well, the power becomes simple. Remember, the power is what? The power, a cool expression for the power is F times V, right? Well, for our case, it's the tension times the velocity. Here's the tension, and the velocity is given to us. Simple. Becomes a really easy problem. So we have 5,809.8 times the velocity 3. So I'll multiply that by 3, and I'm going to get 17,429.4 watt. There we go. That's how much energy is being consumed, or in other words, 17,429.4 joules per second. That's how much power the motor is using to lift itself and the passengers at a speed of 3 meters per second. You got it? Okay. All right, one more problem I want to work on. This one is a toughy one. I don't think I have it assigned as homework. It's problem number, it's not exactly the same as that one, but it's problem number 69 in the book, and it is under the category challenge problems, and it's level 3 difficulty. Okay, so it's a tough problem, similar to the one that I'm about to do, but I don't think this is homework. I don't remember. I usually solve this problem in class, and but we don't have class anymore. Isn't that sad? So anyway, I am very saddened about that. You know that really, I would rather be with you guys in a class and you know, whiteboard and you know, rather than this. Anyway, so I have this problem for you. I need to come downstairs and tell him to shut up. Okay, here's an example. This one is not terribly easy, so you need to pay attention to it. This is the last problem, I think. Yeah, we'll just make it the last problem. Yeah. If I have time, I'll give you one more. But anyway, okay. It goes like this. Imagine I have a pendulum, or, yeah, we'll call it a pendulum. And the pendulum is situated like that. Here is the pendulum. So I'm holding it in my hand. Here is it. In a horizontal position. I'm about to, you know, let go, and it's going to swing down. You got that? Okay. So let me just put a vertical line here to make things easy. And let's assume that the length of the pendulum is L, and it's initially at 90 degrees here. Okay? This is 90 degrees. Down this vertical line, okay, there is a peg or a pin right here. I'll put it right there. Okay, that's a peg or a pin. I don't need to write it down. Okay, that's a pin, peg, or a pin. Okay, and what's going to happen when the pendulum swings down like that? Okay, well, what's going to happen is going to hit the peg. Okay, I think I made it too tall. You know what? I'm going to put the peg here. Hold on. It's so noisy. Okay, so I'm going to put it right here. Here's the peg. Okay, and so what's going to happen is that the pendulum is going to hit the peg, and it's going to go like that. Oop. I'm trying to be as careful as possible. I want to be as accurate as possible, rather. And it's going to come here, and then, right, instead of saying, it's going to hit it. So it's going to be here, and it's going to hit it, and it's going to swing up like that. You see what I'm saying? Everybody see that? Okay? All right. So here's the statement of the problem. Assuming that the initial velocity here is 0, okay, and it's 90 degrees. Oh, I forgot to mention. Okay, so we said that the length of the pendulum is L, and the distance from here to the peg is D. Got it? That's a D. He says, show that, here's the statement, show that it will swing full circle around the peg only if D is equal to 3L over 5 as a minimum value. I want you to stop the video and think about that. I want to be able to see what's going on. Okay, so here is the cable of the string of the pendulum. It swings down. It's going to hit the peg in the middle. Okay, and it's going to swing up just some part of it. Now imagine if I have this peg to be, say, right here, somewhere here. It's not going to swing full circle. At a certain distance, d, it's going to swing like that. Full circle. So it's going to go here, going to go, and then that, there, full circle. And that the minimum distance d must be, show that it must be this number. We want to show that this number. Got it? This is similar to problem number 69, I said. Page 260. It's a little bit different, 69, but if you know how to solve that, you shouldn't have a problem doing the other one. Okay, how do we do it? First of all, now if he says, well, let's use the conservation of energy, right? So what is the total energy of the bob? We are basically following the bob, right? We're assuming the string is massless, so we're following the mass of the bob. The mass of the bob is, we'll call it m. Okay. So right here at this position, before I let go, the total energy here is just mgh. And remember, this is our data right here. So that's u is 0, right? So mgl. Okay. Now I want to know what this here. Now, in order for it, here is the key. In order for the bob to make full circle, the velocity here cannot be 0. Make sense? See, if it's 0, let me call this position. Let me call it position C. Okay, this is position B here. This is position A. V sub C cannot be 0, because what will happen if it's 0? It's just going to fall down, straight down like that. That's it. So it has to have certain minimum velocity V sub C here in order for it to complete one circle. We have to calculate that VC. In other words, at point C, remember this is at A here. So this is at A right here. Okay, this is at A. At C, what's going on? Well, let's see. I have 1/2 mv sub c squared. I don't know what v sub c is, but I need it. Plus, I still have the height. Remember, this is my datum right here. That's my 0 potential. So it's this height. Well, what is this height? Well, from here to here is L, correct? And then from here to here is D, right? So from here, well, what is this from here to here? That will be L minus D, and this is also L minus D. So it's just going to be mg, what is L minus D? So that's going to be 2L minus D, correct? Make sense? So the height here, from here to there, 2L minus D. Everybody got that? Okay. So the problem here is to find what is V sub C. How do I find that? Again, I wish we were in class. We would sit down and I would have you guys discuss this one with each other and see how you can come up with an expression for V sub C. But in this situation, we can't do that. So how do I find it? Here's how you find it. You cannot find it with the energy method. You have to go with the force method. See, in order for V sub C to be non-zero, well, look at the bob here. Here's the bob of the pendulum. It has the weight of the pendulum, of the bob, excuse me, is mg like that. And this is V sub C. The mg here will play the role of the centripetal force. So here, if I use sum of the forces equal ma, where a is the centripetal acceleration, so that's just going to be mg, I'm ignoring the minus sign, equals to m v squared over what? Over r. R is what? Well, R is the radius of that circle, which is this one. And what is that? That's L minus D. And this, of course, V squared is EV sub C. The masses cancel out, so I get V sub C squared is equal to G L minus D. There we go. I have an expression for it. The difficulty of this problem is this. If this doesn't come up in your mind, you cannot solve the problem. This have to come up to your you have to think about that in terms of centripetal forces. Otherwise, you're not going to be able to solve the problem. And that's the difficulty of problem number 69. The same thing. You please look at it, and if you cannot solve it, you put it in the discussion forum. Tell me, and I will be more than happy to solve it for you. Okay, so now I go back to my energy equation. So I have here, so I have mgl equals to 1/2 m vc squared is that right now, plus that mg 2l minus 2d, right? So the mg cancel out for all of them. I end up with L equals to, insert this half in here, it's going to be 1/2 L minus 1/2 D plus 2L minus 2D. Is that okay? So I have L, I'm getting tired, I'm sorry. And then I have here 1/2 L plus 2L, that would be what? 5 over 2L. And then minus 5 over 2D. Again, move this over here, L minus 5/2 L equals minus 5/2 D. This will give me minus 3/2 L equals minus 5/2 D. 2's cancel out, the minus cancel out, therefore L is equal to 5 over 3D. Or D equals 3 over 5L. And that's what he was asking for here. He said, show that it will swing a full circle around the peg only if D equal to 3L over 5 as a minimum value. And there we go, we got it. We got it? Okay. Okay, I think I'm going to stop here, and please feel free to post whatever problem that you need help with. And I encourage you to be active in that discussion forum that I have just created this week. I created it temporarily. I want to see if you guys like it. If not, I may not post it again, but I want to try it this week and see. Again, I'm going to look at it. I would rather see you guys discussing problems together, okay, rather than me. But I'll be reading it on a daily basis. Even if I don't make any comment, it doesn't mean I'm not reading it. I'm just kind of monitoring you and how I'm seeing how you are interacting with each other. But anyway, it's optional. I absolutely don't need to do that. I know you have enough work in your hand, but it's available for you. Okay, it's available for you. Okay, that's it. And have a wonderful day, wonderful week, and bye-bye.